Hello everyone and welcome back. In this video we're going to introduce random variables. Random variables will play a vital role when we begin to cover inferential statistics, so it will be important to understand what they are and how they are used. So what are random variables? Well, they are a variable that takes on any value that results from a random event, and we denote these by using capital letters. Random variables can be discrete, which can only take on a distinct number of values, or they can be continuous, which can take on any range of values in an interval. Now, the way that we treat random variables will depend on whether they are discrete or continuous, and we will begin with working with discrete random variables first. Now, a probability model, or a probability distribution, is a function that assigns a probability p with each value of a discrete random variable capital X, and we denote the probability by capital P of capital X equals lowercase x, or simply P of lowercase x, where the lowercase x represents one distinct value of the random variable. And if we're dealing with continuous random variables, then we will be using a density curve to assign the probabilities. So let's look at an example of a random variable and its probability distribution. Let's consider tossing a coin 3 times, and we'll let the random variable x be the number of heads. So in this case, after we have tossed the coin 3 times, our random variable can take a one of 4 possible values, and they can be 0, which means that there are no heads, or there could be 1, 2, or 3 heads. Now we want to find the probability for each value of x, and we'll do this by listing all of the possible outcomes. So let's first write out our sample space S for 3 coin tosses. So here there are a total of 8 possible outcomes. And so we'll list all of the outcomes for our sample space. So one possibility is that all of the results are heads. Another possibility is that we have 2 heads and 1 tails. And there are 3 possible cases for 2 heads and 1 tails. So this could be where the first 2 results are heads and the third coin is tails. We could have heads, then tails, then heads, or we can have tails, then 2 heads. Next, we can have 1 heads and 2 tails, and there are 3 possible scenarios that this can happen. So we can have that the first coin is heads, then the next 2 are tails. We could have that the first coin is tails, then heads, then tails, or we can have 2 tails, then a head. And lastly, we can have all tails, and these are all of the possible outcomes from 3 coin tosses. So now we will write the outcomes that correspond to each value of x. For the value of 0, this means that there are no heads from our coin tosses, and the only outcome for this scenario is that they are all tails. Now for the value of 1, this means that there is 1 heads from our 3 coin tosses, and we know from our sample space that there are 3 possible outcomes. We have heads, tails, tails, or we could have tails, head, tails, or tails, tails, and heads. For the value of 2, there are 3 possible outcomes for 2 heads, which are heads, heads, tails, heads, tails, heads, or tails, heads, heads. And lastly, for the value of 3, there's only 1 outcome for 3 heads. Now, because the coin is fair, this means that each outcome will be equally likely, and so we can calculate the probability by taking the number of outcomes and dividing it by the total possible outcomes. So the probability for x equals 0 is going to be 1 out of 8. The probability for x equals 1, well, there are 3 possible outcomes out of a total of 8, so its probability will be 3 out of 8. Similarly, for x equals 2, there are 3 possible outcomes out of 8 in total. And for x equals 3, there is 1 outcome out of a total of 8. And so this is the probability distribution of x. So now let's use this distribution table to find the probabilities for the following events. So what is the probability that no heads occurs? Since x represents the number of heads, this means that we're looking for the probability that x is equal to 0. And so using our table, we know that the probability is 1 out of 8. So now what is the probability that at least one head occurs? So here we're looking for the probability that x is greater than or equal to 1. So at least 1 means it could be 1 or greater. And to find this probability, we take the probability that x is equal to 1 plus the probability that x is equal to 2 plus the probability that x equals 3. And using our table, this is equal to 3 out of 8 plus 3 out of 8 plus 1 out of 8. And in total, this gives us 7 out of 8 as the probability. When we're working with a probability distribution, we can define the mean and the standard deviation in a similar manner back in chapter 1. Now the expected value E of x of a discrete random variable is its theoretical long-run average, and it is the mean of its probability distribution. And we can calculate the expected value as follows. So the mean, mu, which is also known as the expected value E of x, is equal to the sum of x times P of x. So let's take a look at an example of finding the expected value for the probability distribution in our 3 coin toss example. So to find the expected value, we take each value of x and multiply it by its corresponding probability, and then we add up all of these values. So for our coin toss example, we have a value of 0 for x, and we multiply this by the probability, which is 1 out of 8. And then we add this to our next value of x, which is 1, and we multiply this by its corresponding probability, which is 3 out of 8. And then we add this to 2 times its corresponding probability of 3 out of 8. Then we add 3 times its corresponding probability, which is 1 out of 8. And so simplifying, we have 0 plus 3 out of 8 plus 6 out of 8 plus 3 out of 8, which becomes 12 out of 8, or 1.5. So the expected value of our random variable x is equal to 1.5. So let's think about what the expected value means for our example. Recall that our random variable x represents the number of heads for 3 coin tosses. We calculated the expected value to be 1.5, and this is the theoretical long-run average of the random variable. So what this means is that on average, we should expect 1.5 heads over many, many trials for 3 coin tosses. And this should make sense since we assume that our coin is fair, so we should expect heads to appear 50% of the time. And 50% of 3 is 1.5. Now we can define the variance of a discrete random variable to be the expected value of the squared deviation from the mean. And so the variance, which we denote by sigma squared, or var of x, is the sum of the squared deviations from the mean multiplied by its corresponding probability. And the standard deviation is the square root of the variance. So let's find the variance and the standard deviation of the random variable x for the 3 coin tosses example. So to find the variance, we will take each value of x, subtract the mean, square it, and multiply it by its corresponding probability, and then add up all of these values. So for our first value of x, we have 0. We calculated the mean to be 1.5. So we squared this difference, and we multiplied this by its probability, which is 1 out of 8. Then we add it to the next value of x, which is 1. We subtract the mean of 1.5. We square the value, and then we multiply this by its corresponding probability, which is 3 out of 8. Then we add it to our next value of x, which is 2 minus 1.5 squared times 3 out of 8, plus 3 minus 1.5 squared times 1 out of 8. And if we perform this calculation, we'll end up with a variance of 0.75. And now to find the standard deviation, we take the square root of the variance. So the square root of 0.75 will be approximately 0.87. So now let's consider another example. Suppose that you're playing a game where you have a 65% chance to win $10, 25% chance to win $20, and 10% chance to win $50. So what is the expected value of your winnings? So let's first write the probability distribution table. So here we're going to let x be our winnings for each game. So we could win $10 with a probability of 65%, or 0.65. We could win $20 with a probability of 0.25, or we can win $50 with a probability of 0.1. So now we can calculate the expected value. So we take each value of x and multiply it by its corresponding probabilities, and then sum them. So we have $10 times 0.65 plus $20 times 0.25 plus $50 times 0.1. And if you perform the calculation, we end up with 16.5. So this tells us that if we were to play this game over and over, then the average amount of our winnings per game is $16.50. Now let's suppose that we had to pay each time in order to play this game. So what is the most that you should pay in order to break even? Well, because the expected value is $16.50, which is our average winnings per game, then the most that we should pay in order to break even is $16.50. And this will conclude our lesson for this video. In the next video, we will look at some of the properties of the expected value and variance, and I'll see you then.